Mitra, are you able to hear me?
Yes, sir.
Okay, fine. Okay, fine. Let's start then. Even before moving forward where we left yesterday, let's try to recap to answering these questions. Okay. What is y is equal to f of x equation is called? Is it straight line? Function of x, where y is the dependent variable, x is the independent variable. Based on the function what you are applying on the independent variable, the values of the outcome, which is nothing but, just give me a second, friends. Sorry, guys, just give me a minute. Guys, anybody has got the link for this session? Online folks? Any one of you have got the link that you have used to join this session?
We are using directly from that live classes.
Okay. Sorry? Oh, here, yeah. That's right. Okay, fine. Sorry about that, friends. Guys, are you able to hear me? Online folks. Okay, sure. Okay. When y is equal to f of x, y is the dependent variable whose values are going to be dependent on the function that you are applying on the x values. Okay. Now, the second question. What should be the relationship between input and output variable to start with regression? What should be the basic relationship that has to be existing to start with regression between the input variables and output variables? Online folks? Continuous, yeah, linearity is the right answer, Aditya. So the input variables needs to maintain the linear relationship with the output variables to start with regression. Where the data type of y has to be continuous if you'd like to start with linear regression, right? And what are y and x called as in the above equation? What is y and what is x? Y is dependent variable or the output variable, and x is the independent variable or the input variables. How to evaluate the relationship between two quantitative variables? If you'd like to identify the relationship between two quantitative variables, how can you identify? Even before that, what are quantitative variables? Yeah, which you can represent in digits in the form of numerical digits. Okay. So how can you identify the relationship between two variables? Yeah, what do you call that? The coefficient of correlation coefficient. Okay, the small r. Okay. Which plot do you? That's the scatter plot you make use of to understand the relationship. By the scatter plot, what all the information it conveys? If you're drawing scatter plot between two continuous variables, what all information it tells you? The direction of the relationship and the strength of the relationship, right? Now, can we plot gender and salary of people in scatter diagram? No, right? The reason? So basically, the variable gender is not continuous. Scatter plot can be drawn between two quantitative variables or the continuous variables, right? So gender is a categorical data, male, female, right? How do we measure the correlation between two variables? How do we bring the objectivity to understand the relationship between two variables? How do we bring the objectivity? Because by looking at the scatter plot, different people would have different opinions in terms of whether they're strongly correlated or moderately correlated, positively correlated. How do we bring the objectivity? Correlation coefficient, right? Correlation coefficient. Okay. What is the range of small r? R takes the values between -1 to +1. What is the thumb rule for R for a relation to be called as strong relation? More than? Which should be more than 0.85? Is it R? Is it small r or capital R? What it should be? So to call the relationship between two variables as strong relation, the value should be more than 0.85. Which value has to be more than 0.85?
Modulus of R, smaller.
Yes, exactly. The mod of R should be more than 0.85. Only then you can call the relationship as strong relation. What is the equation of a straight line? Y is equal to mx plus c. What is y here? Dependent variable. X, independent variable. What is c here? Intercept of? No, is it which intercept? Is it x-intercept or y-intercept? It should be y-intercept. What is m? Slope. Slope of x, the straight line, that the independent variable maintains with the output variable y. What does OLS mean? Ordinary least square technique. Is that an error? Yeah, that's an ordinary least square technique. What do we use that for? To find the best fit line. Because there are various number of lines that can be drawn that goes through the data points. But out of all the possible lines that could be drawn, we choose the best fit line based on the OLS technique, ordinary least square technique. So whichever the line maintains the least distance with all the data points will be chosen as the best fit line. Because of the fact that we're going to make use of this equation to come out with the predictions of the output variable. Is it good to have more distance between the predicted values and actual values or less distance? It should be the least distance. And that is the reason we are selecting a line which maintains the least distance with all the data points. Okay, fine. Now, let's start with multiple linear regression. When do we go for multiple linear regression? What should be the data type of output variable y? What should be the data type of output variable y? It has to be continuous, right? And based on the number of input variables that you are using to predict your output variable y, then we decide to go between simple linear regression or multiple linear regression. If the number of input variables are more than one that you are using to predict y, irrespective of whether they are continuous or discrete. We still go for multiple linear regression. If they're continuous, perfectly fine. If the input variables are discrete, what should we do? We create the dummy variables, right? And yesterday we looked at different approaches for creating the dummy variables and which approach is the best among that, right? So this is how we need to create the dummy variables. For each class value, within the variable for which we are creating the dummy variables, we need to see how many unique classes are existing. Each of these unique value is called as a class when it comes to the categorical data. There's a typical categorical variable, make of a car. So how many classes we have in this? 4 classes: petrol, diesel, CNG, and LPG. To create the dummy variables, we need to come out with 4 dummy variables, which is very much specific to each one. Should be the specific dummy variable for each class, right? Wherever we see the relevant class value, we mark it as 1, all remaining 3 as zeros for that record. And this is how we need to create the dummy variables, so that we don't get biased towards giving more weightage for a particular class than others. If we go the typical approach of creating the dummy variables just by assigning 1 and 0 within the same variable, or 1 and 2, that means we are giving more importance for one class than the other. That means we are getting biased towards a particular class. We don't need to be. Okay? We have to represent all the classes with an equal importance. Only then your algorithm will be able to understand what exactly that you are trying to represent as part of that record. Clear? Now, this is the case study that we are going to solve for multiple linear regression, wherein this is a cars data set, wherein we have 5 variables in that: volume, horsepower, mileage per gallon, speed, and weight. What is the output variable in this that we need to predict? MPG, mileage per gallon, is the output variable. So this is our Y. And these are X1, X2, X3, and X4. Right? Even before going ahead and build a model for this data using multiple linear regression algorithm, we need to identify, we need to understand various properties that have to be satisfied when we are dealing with linear regression with multiple input variables. This is very, very important, friends. These are called the regression assumptions, linear regression assumptions. The 4 levels of assumptions that we need to make sure they are satisfied before you consider the result of your model is very good. Only even though the model is giving somewhat reasonable or acceptable accuracy. How do we measure the accuracy of a linear regression model? R squared value, multiple R squared value, right? Even though the R squared value is acceptable or little higher, you cannot straight away consider that model for pushing it into the production. That has to be, the model has to satisfy all these assumptions. Only then you can call that as a very good model. These assumptions are categorized into 4 levels. The first one is about parameters. What are parameters in this equation? Beta naught, beta 1, beta 2, all the coefficients are called as parameters. They can be called as parameters or estimators. All these parameters have to maintain a linear relationship with what? With the output variable y. Okay. And it's not just the parameters needs to maintain the linear relationship. Even your input variables, x1, x2, x3, and so on, even they have to maintain a linear relationship with the output variable y. How can you check the linearity? You need to plot. Which plot? Scatter plot gives the relationship, but the linearity? QQ plot, right? Where we will have a reference line. We see whether majority of the data points in the range of IQR, interquartile range, are falling on that line or not. Then accordingly, we decide whether the data is following linearity or not. Clear? Now, the second section of the assumptions are about the errors. Now, when do we get to see the errors? Is it before building the model or after building the model? After building the model. Once we build the model, then we will have the predicted values. And the difference between your actual values and predicted values become the error. Correct? But let me ask you another question. If I would like to check the linearity between the parameters and the output variable and the input variables and the output variable, can I check this before building the model or after building the model? There are two parts to it. One is checking with respect to the input variables x. Second part is checking with respect to the coefficients or parameters or estimates. If I'd like to check the relationship of each of the input variable with the output variable, you can perform that as part of bivariate analysis, which is very much part of your EDA. You don't need to build the model for that. But if I'd like to check the linearity of these coefficients or parameters or estimates with the output variable y, you have to build the model. Only then the coefficient values will be determined, right? Now, coming back to the assumptions about the errors. Hope I'm clear, friends. Any doubts you can ask me so far. Online folks, are we clear? Okay. Assumptions about the errors. The most important properties that you need to validate once the model is built. The first and foremost assumption is about the errors should follow IID property. IID is nothing but independent and identically distributed. Independent and identically distributed. If I plot the errors, what should be the mean of the errors? What will be the mean of the errors? Should be 0, right? That's what the second property is. If I plot the errors across the mean 0, each error should be independent compared to other errors. They should not maintain any sort of dependency among the errors. Okay. Then what is identically distributed? If you plot these errors, across the mean value 0, at any point, the shape of your distribution, error distribution across the mean 0 should reflect similar. So this is how the errors are plotted in this. That means the number of errors that you have are symmetrically distributed across the mean 0. Otherwise, if it maintains any patterns, if they are symmetric, you have more errors plotted on this side, very less few errors on this side. That means they are not identically distributed. Okay. And the mean of the error should be 0. And the error should maintain a constant variance, which is called as homoscedasticity. What do we mean by constant variance? So when I plot these errors, the variance is nothing but spread of the data, right? They should maintain a constant variance. The spread here in the starting should be same as the spread what you observe in the other regions. Clear? If the errors are spread like this, is the variance is constant in this case? No, right? Looks like a cylindrical shape. The variances keep increasing as you move forward on the x-axis. The variance, the spread here, what you are seeing is way higher than the spread what you are seeing in the initial phase. Correct? Is this an expected behavior? Having an inconsistent variance? Having a consistent variance, constant variance is an intended behavior. If you have inconsistent behavior of the spread variance, then it is a problem that you need to deal with, and that problem is called as heteroscedasticity. Homoscedasticity is an expected behavior. Heteroscedasticity is a problem that you need to deal with. How do you deal with heteroscedasticity problem? You have considered all the features that you would like to consider or you would like to place as part of the model building process. And you build the model, you have predicted the output variables, output values. Now you are comparing the actual values with the predicted values, thereby you are getting the errors. If you get to observe that the errors are following heteroscedasticity problem, how do you deal with that? How do you solve that problem? Transformation. Transformation is a technique that you need to use to remove this heteroscedasticity problem. Thereby you make sure the errors follow homoscedasticity behavior. Am I clear? Now, these errors should be independent of each other. There should not be any dependency with errors of one observation and the errors of other observations. If at all they are not independent, that means there is a sort of dependency existing. That means the errors of some observations are influencing the errors of other observations. Then that is also a problem. There shouldn't be any dependency between the errors. The problem is called as autocorrelation. But generally, the data that we deal with in discussing the initial algorithm is called cross-sectional data. So if you look at, we have worked out a problem, we have solved this linear regression, right? We have built a model using linear regression algorithm. What is that? The output variable we predicted using linear regression. Adipose tissue. Using which input variable? Waist circumference, right? So in the data given to us, apart from this adipose tissue and waist circumference, do we have any other details? No, right? Just 2 columns were given. Was there any time associated at what? When the respective patient's measurements have been captured? No, right? If we don't have the time associated in the data, then you call that data as cross-sectional data. If there is a time associated, let's take the case of capturing the sales of an organization at regular intervals across a time period of an year. Let's say every month you are capturing the sales. That means there is a stipulated duration that exists between the two events at which you are capturing the data. That's called time series data. But when it comes to the autocorrelation problem, generally you tend to see this in time series data. Cross-sectional data, you don't get to see this problem. Okay? When we discuss about time series forecasting, we'll discuss more about how to deal with this. And coming to the third section of assumptions. These assumptions are laid out for the predictors. What are the predictors? What are the predictors in your equation? Predictors are nothing but independent variables, x1, x2, x3, and so on, right? These predictors should be non-random. Why are we saying they should be non-random? We should consider only those variables that are relevant for your business problem solving. There is no fun in including all the data that you have. Okay? And they should be measured without any error. The actual data that is given to you, they should be measured without any error. If your input data is accurate enough, only then even your output will be accurate. So hence make sure while you collect the data or as part of the pre-processing, if you're coming out with any derived variables. Derived variables are nothing but the variables that you are deriving based on the base variables that you have, based on other variables given to you. Let us say, if you are given a date column, you feel there is some sort of correlation among the days of a month, the way the data is changing. Then you decide to split the date column into 3 separate columns. One is the day of the month, second one is the month of the year, third one is the year. Okay, these are nothing but the derived variables, but that's a very simple example. But to come out with the derived variables, most of the times you need to have a bit of domain expertise. If you're working on manufacturing, in terms of predicting the life of a battery for a machine that's being used, the various things that comes into the picture. Okay, you might need to come out with altogether a new variable based on certain formula, physics-based formulas. Maybe energy, maybe the temperatures, whatever. Okay, that's why you need to have a bit of domain expertise. Only then you can understand what kind of new variables that you can create still that makes sense towards the business problem what you are solving. Okay. Now, coming to the third assumption of predictors, They should be linearly independent of each other. They should be linear at the first place, and they should be independent of each other. If they're not independent, then it is also a problem that you need to deal with. The problem is called collinearity problem. Means your x1, x2, x3, the input or independent variables needs to maintain a linear relationship with the output variable. They should not maintain any sort of relationship among themselves. If x1 and x2, the two input variables, if they are getting into a high level of correlation or high level of relationship, that's why it is called as a collinearity problem. But is that not expected? We'll come back to that point. Okay. Now coming to the assumptions about the observations. What are the observations? Observations are nothing but the rows in our data, right? The actual values. They should be equally reliable. That means you shouldn't be biased towards a class of variables, right? Typical example of creating this dummy variable. We are giving equal importance for each and every class. So these are all the assumptions that needs to be satisfied, though your model's accuracy is acceptable enough. Only and only once you check whether all these assumptions are satisfied, you cannot call that as a good model. Am I clear? Now coming back to the collinearity problem. Online folks, any questions before I move forward? You need to understand this very thoroughly. Cannot afford to go wrong in terms of understanding these assumptions. Yeah, obviously. We are going to see. Practically, we are going to see. How do we validate all these assumptions? If at all, a model which is failing to satisfy certain assumptions, how do we deal with that? We're going to see all of them. Just we will see. Okay, don't be hurried. Coming back to the collinearity problem. Now, what is the output variable in this data? MPZ, right? And the remaining are input variables, x1, x2, x3, and x4. Now, what should be the equation to predict the output value of y? What should be the linear equation? Linear regression equation. Y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4. Clear? So now, if you replace what is y, what is x1, x2, and so on in this equation, then effectively your equation becomes MPZ is equal to beta naught plus beta 1 volume plus beta 2 HP plus beta 3 speed and beta 4 weight. What is the collinearity problem that we are discussing here? If the input variables gets into a relationship among themselves, ideally these input variables should be independent, linearly independent. They should be linear with the output variable, but they should be independent within themselves. But looking at, if I take two variables out of these four input variables, which are nothing but volume and weight, if the volume of a vehicle is increasing, what could be the relevant change in the weight of the vehicle? It would increase. If the volume is decreasing, weight obviously decreases. That means, are these two variables are correlated or not? They're having a highest positive correlation. If one is increasing, the other one is increasing. May not be at the same magnitude, but there is a relevant change, but towards in the same direction. If one is increasing, the other one is increasing. If one is decreasing, the other one is also decreasing. So is this not a collinearity problem? Exactly, that's what the collinearity problem means. But is it expected, or do you need to go away from this problem each and every time you observe such relationship between independent variables? It depends. If it makes sense from the business perspective. And obviously, if we take the other two variables, horsepower and speed, if the horsepower of the vehicle is more, would the speed increase or decrease? It would increase. If the speed is decreasing, what does that mean? Don't have enough horsepower to support the speed at which you would like to go, right? Both of them are also positively correlated. So we need to look at the business objective that they are fulfilling before talking about removing the collinearity problem. We are going to see practically, okay? So any questions, friends, before I move forward to look into the practical aspect of solving this case study? Sorry? No, you don't need to. Because generally, as from a mathematics perspective, the y is equal to beta naught plus beta 1x plus epsilon is the equation, right? That epsilon was taken on the right hand side to balance the deviation that you could go with your prediction. Okay. If you know what is the error, then you can balance both the sides, right? Okay. Now, let's look at the data of this cars. Now, can you tell me the data type of each of these variables? Is it discrete? It's also continuous, right? You can still represent them with 49.0. Still, it makes sense. And even volume also, yeah, still continuous. So all the variables are continuous. Align, folks? Do you agree?
Yes.
Okay, fine. So now, MPG is our output variable that we are predicting. Y. HP volume, speed, weight, so all these four are the independent variables or the input variables, which are again continuous. If the output variable y is continuous, irrespective of the data type of your independent variables, in order to predict the output value y, which algorithm do you go for? Multiple linear regression, right? Just pay attention, your friends. So I'm just loading the same data of cars.csv. Setting the working directory, then reading the data CSV file directly into the variable called cars. So how many variables and how many observations I have? So 81 rows and 5 variables are there. These variables are also called as features or dimensions of your data. If anyone asks you what is the feature set you have used to solve a problem, typically what are the variables that you have used? That's it. Okay. So we're just viewing the cars data. It's the same data that we have seen in the spreadsheet. Now I'm attaching this cars data so that we don't need to repeat the data frame name every time I refer a column from that. So when I attach something, that stays in the RAM as long as the session is live. What do we use this QQ norm for? Which graph? Linearity. QQ plot, right? Quantile plot. You can just need to explore a bit about that function. What all arguments you need to pass in. Can make the graphs very beautiful. Okay. But looking at this, do you think the HP data is following normality? How many of these data points are falling exactly on the reference line? Very less, right? So some of us might feel it's close by to that reference line, that is still fine. And that's where we need to look at the other measures. Now, what does the summary function gives? The basic statistics information, right? Now, by looking at the summary, do you see any issue with respect to the data that's being pulled by all these 5 variables? What do you understand by looking at the basic stats? Don't tell me the minimum value first quarter and all, because that is anyway, we can see it. The distribution of the data. By looking which of these factors, which of these values, you will be able to understand the distribution of the data. the minimum and maximum values, the range, right? And do you see any issue just by looking at this information that you think you need to handle? Can you come again? In HP? So you are saying the HP values are comparatively higher on the scale with the other variables. Outliers, how can you say? Exactly. Okay. So the mean and median are closer to the minimum value, and thereby you have outliers existing towards the right of the mean or median. So which skew do you call that as? Positively skewed, right? But other than that, just by looking at the basic stats information from each of the variable, we can also understand what is the scale of the values. Because we are considering all these 4 independent variables together to predict the output variable MPC. That means we are combining all the 4 input variables data and submitting that as an input for the algorithm to predict MPC. If there is a scaling issue, if one value is in thousands, the other value is in tens, you definitely need to fix such issues. Okay. Now, with each input variable, we are checking with the output variable how the plot looks like. What does this give? The plot between 2 variables. Scatter plot. So when the HP is increasing, the mileage is decreasing. But is it linear? Is it very strong or moderate relationship? We cannot really say that until and unless we see the correlation coefficient. Similarly, for each input variable, you need to check how the relationship is existing. So what kind of relationship do you think that volume is sharing with the MPG? Negative? Negative correlation. So definitely it is not strong. Right? Fine. Since we have only 4 independent variables, we have all the time in the world to be able to check how each of the variable is related with the output variable, or how each of the variable is maintaining a relationship with other independent variables, right? But what if you are given, you have 100 variables or 500 variables in your data? But that's where space function will be very useful. By looking at the pairs function, we can understand what kind of relationship each input variable is maintaining with the output variable MPG. And this is looks like moderate negative relationship. And how volume is having a relationship with MPG. It's also negative, but it's between a weak correlation and moderate correlation. And SP, speed with volume, sorry, with MPG is also negative. It looks more moderate. How about weight and MPG? The weight of the vehicle is increasing. Would the mileage increase or decrease? It decreases. That's what it has, a negative relationship. But other than checking the relationship of each of the variable with the output variable, do you see any other issue within the input variables? Collinearity. Which variables? Volume and weight. Volume and weight are having very strong positive correlation. So any other combinations you see within the input variables? How speed and HP are having a relationship? Looks like this is also moderate or very strong positive relationship, right? But can we call that as a collinearity problem right now? That depends on the business objective of each of that variables. Okay. Now, to bring the objectivity, you need to check the correlation coefficients. By looking at the correlation coefficients, speed is having a very strong relationship with HP. How do you read this matrix, friends? In the diagonals, you have ones. One is nothing but wherever. How do you interpret this value 1? Perfect, strong relationship. But which variable is having that level of relationship? HP is having such relationship with itself, right? A correlation between a variable with itself is always 1. Hence, all the diagonals will be 1s. Either you can look at the bottom part of it or upper part of it. Right? Here, SP is having a very high, strong positive relationship with HP. And volume and weight is even close to perfect positive relationship, right? So these are all the things that you perform in EDA. You start right from looking at the measures of central tendency, variance, skewness, kurtosis, histograms to understand the shape of the data. All these things you perform as part of univariate analysis. Box plots to understand the outliers, to identify the outliers, right? And the distribution of the data of each variable. Then when it comes to bivariate analysis, that's when you start with the correlation to check the relationship between the variables, right? Now, let's build a simple linear regression model by considering MPG as the output variable, Y, tilde all other input variables, x1 plus x2 plus x3 plus x. Let's build a base model. Now let's see the result of this. What is the first thing that we need to check when we build a linear regression model? What do we need to check? The first thing. The significance of each of the coefficients, right? All these variables coefficients are significant. All folks, all these variables coefficients are significant or not? What do you check? Based on the p-value, right? The probability value. What are these probabilities? The probabilities are nothing but the chance of going wrong. Okay. So we need to compare these p-values with the alpha values. What is alpha value? If it is not given, 95 is what? 1 minus alpha or alpha? 5%, 0.05. So we need to compare the p-value of each of these coefficients with the alpha value. Is the p-value for intercept, which is beta naught, is it lesser or greater than alpha value? This is lesser. Lesser, right? Slightly lesser, 0.404. So any one of these are more than significance level. Zero point 5563 for the volume and 0.8136 for the weight. So only these two variables are not significant. These two coefficients are not significant. What does that mean? When the coefficients are not significant, what does that mean? That means we cannot consider these values as the coefficients of those variables in our regression equation. But by making use of these coefficients, let's say if all of them are significant, what is the equation you are going to frame? What is the regression equation that you're going to frame? Your y, nothing but MPG is equal to beta naught. What is beta naught? We need to take these estimated values. 30.67 plus beta 1 x1, right? Here, what is beta 1? Minus 0.3360 minus 0.336 into volume minus 0.205 into HP plus 0.395 into SP. SP is nothing but speed plus 0.40 into weight. So what is it telling? If anybody asks you what sort of influence that volume is having on MPG, how can you interpret it? If the volume is increasing by 1 unit, your mileage is decreasing by 0.336. Clear? And this is how you need to interpret. So, however, of course, we cannot consider these coefficients in our equation for volume and weight because they are not, the coefficients are not significant, right? If they are significant, what does this 3 stars means? 3 stars means they are significant. 1.4 e power minus 6. How can you write this same thing? 1.4 into 10 power minus 6. This is nothing but 0.5 zeros in the 6th position. You will have the number coming 1, 4. So is this less than alpha or more than alpha? Very much lesser than alpha. It's pretty much close to 0, this value. That's why whatever the values that are pretty much close to 0 will be represented with 3 stars. The ones which are close to 0.001 will be represented with double star, 0.01 single star. The values which are very close by to the alpha value, significance level, 0.05, will be represented with dot. So whichever is more than significance level will be represented with the quotes. Okay. But what is the overall accuracy of this model that we built? Multiple R squared value, right? Multiple R squared value will be taken as the accuracy of the model because of the fact that multiple R squared value talks about the percentage of the data points are falling on the equation, the straight line equation which you framed. 77% of the data points are falling on this equation. That means there is still 23% of the data points which are far away from this line which you have drawn. So that means that is where your prediction is going wrong in comparison with the actual. Am I clear? What does this adjusted R square talk about? It's also a R squared value, right? The name is there. How can R square be error? So far we are treating R square as the accuracy of the model. But what does this adjusted R square indicate? Multiple R squared value, irrespective of the relevance of the new variable that you are adding to the equation. So far you have 4 variables, 4 input variables: volume, horsepower, speed, and weight. Let us say you got some new variable, another variable, and you added that to this equation. Irrespective of the relevance of the new variable that you are adding to the equation, multiple R squared value will keep increasing or max to max. It would stay at the same value. It doesn't decrease. But whereas when you add a value which is irrelevant to the equation, your adjusted R squared value starts penalizing the model. If you add a completely irrelevant variable towards the business problem what you're solving, your adjusted R squared value starts decreasing. So that is where, as part of the feature engineering, through forward selection, backward elimination, and stepwise selection techniques, using adjusted R squared measure, you can understand the relevance of a new variable that you are adding. If the adjusted R squared value starts decreasing, then better you drop off that variable which you added. And thereby, you keep only the important variables that are required for your prediction in your equation for predicting y. Okay. Hmm. Hmm. Hmm.
Your adjusted R square decreasing, so you can get it, but then it won't show the
Okay, fine. So, considering the problem what you are quoting, generally, if I have any promotional coupons, would they tend to increase the sales or decrease the sales? Yeah, I do agree. If the profits are decreasing, that's perfectly fine. Are they meant to increase the sales or decrease the sales? Generally, sales should increase by considering a particular coupon, right? If the sales is increasing, but still, if your adjusted R square is decreasing, it will not decrease if, as long as you are considering a variable which supports towards a change in the output variable. But only and only, but coming to the business teams, they might come out, oh, why don't you consider that variable? I feel even that variable is also relevant or important for solving this business problem. There's no harm, just consider it. Consider it. If it starts decreasing, you can go back and say that, yeah, I tried that, but statistically, there is no much relevance of that new variable which you suggested to me consider. In fact, I tried it. It's a very good suggestion. I tried it, but it's not helping us towards our prediction. Okay. All these theories based on which what we are discussing here were already proved on thousands of instances. This is not something we are talking on the air. There's a baseline proof in terms of how this adjusted R squared works or multiple R squared works. Not only this, whatever stats relevant, whatever we are going to discuss from here onwards, all of them are proved, and you would definitely see when you start experimenting yourself, you would see the similar impact. Okay. The adjusted R squared value, when you keep adding a new variable which is not relevant, it starts penalizing the model. Thereby, you can understand whether the model is relevant towards the prediction or not. If it decreases because of adding a new variable, better to drop off that. Or if it increases, that means that is an important variable that you can have towards the prediction what you're working on, right? Okay. Adjusted R squared value would decrease if you add an irrelevant variable. If you add a relevant variable, definitely starts increasing. But for multiple R squared value, irrespective of whether it is a relevant variable or irrelevant variable, if it is relevant, it starts increasing. If it is completely irrelevant also, sometimes it may increase, but it will definitely not decrease. It would stay at the same level where it was, but it will not decrease. So thereby to understand the effect of the new variables that you are bringing into the process of prediction, your adjusted R-squared measure helps you to give an indication whether that variable is relevant or not. But multiple R-squared would not be able to give that indication. So as part of the feature engineering, you need to rely upon adjusted R-squared value to understand the relevance of the variables that you are adding to your equation. But once you are fine, you're done with feature engineering, you finalize the features that needs to be considered for the prediction. And once everything is fixed, so then afterwards, you can keep making use of this multiple R-squared value for comparing the performance of different models, to compare the performance of the models, or if you're satisfied with that level of accuracy in terms of the prediction or not. We are going to see multiple things, okay? Don't want to pour in a lot of stuff while we discuss about the basic things. So we'll slowly increase the complexity level of the discussions so that you can catch up, okay? So alongside of checking the significance of the coefficients, we also need to check the overall model significance. How do we check the overall model significance? By this p-value. Even this p-value should be lesser than the significance level. Nothing but alpha. If the significance level is not given, by default you go with 0.0. Am I clear? Online folks? Am I clear or any questions? Okay, fine. Now we built a very base version of the model. We simply considered all the variables, all the input variables, and we have built a model. But looking at the results of this model, first of all these variables are not significant. All the coefficients are not significant. When all the coefficients are not significant and the overall model is not significant, there is no point in going further towards talking about the accuracy of the model or error of the model, right? So definitely this will not be the candidate model for us. Now, what am I doing? By looking at these results, we already understood that volume and weight are not significant. So that means they're not at all useful towards predicting the mileage. That's not what we are talking about here. Though they might be useful from the business perspective, but to predict the mileage of a vehicle, weight and volume are also definitely related, right? Right? But when you are considering both of them together into the equation, that is when they are causing a poor prediction of the mileage, right? So this is called collinearity problem. They are fighting with each other and they are spoiling an entire team spirit. The typical examples we generally see in our work environment, right? Ego clashes. So that's what is happening is between volume and weight. But how do we deal with this? Now let us check how volume alone, is it helpful towards the mileage prediction or not? Now I'm building another model where I'm considering the output variable MPZ, tilde, input variable, only volume. I'm not considering anything else. Just to cross check whether this variable is at all useful for the mileage prediction or not. Okay. Now let's see the results of this summary of. Now, is volume coefficient is significant or not? It is significant, right? Here, very much significant. But how about the accuracy? That's okay. Still, the accuracy is very low. But first of all, it is significant in terms of predicting the mileage, right? Now let us check for weight. How about weight significance? It is also significant, right? The p-value is definitely lesser than your alpha significance level, right? So both of them, when I'm considering separately, yes, they're performing very well. If I give individual tasks to both the candidates, they're outperforming all others, right? Now, let's see. I'll consider only this volume and weight, but I'll not consider any other variables to see if I give the same task to both of them, how they will perform. What's happening? They keep saying, no, it's not my job. The ball is in your court. Okay. That is the problem. So what should we do now? How should we proceed? Should we remove both the variables from our data and consider only the remaining variables for mileage prediction? Are you able to hear me, guys? Lost the connection for a second. Online folks, are you able to hear me? Okay. So deleting the data should not be an option for you. Let's see how these two are related. Let's draw the correlation between these two, only volume and weight. Very highly correlated that we already seen, 99.9. This time, I built a pairs plot where on the bottom part of it, we get to see the graphical representation, the scatter plots. On the upper part of it, we are getting the correlation values, right? To understand which of the variables are highly correlated or which of them are getting into collinearity problems. Just the simple code that you need to execute. This is the function that's built to build this graph. And we are just including this function panel equal to panel.core. Panel.core is a function name that's used here. Okay. So we have a package called car. CO gives the correlation matrix of the overall data set. If I do R2 peak R of correlation of the cars, it gives the covariance matrix. The above one is a correlation matrix, and this one is the covariance matrix. What do you mean by covariance? What is the difference between correlation and covariance? Correlation talks about the relationship between two variables, two continuous variables, and the direction of, if there is a change in one of the variable, what sort of change the other variable is taking place. Are they both are moving in the positive direction or negative direction? Yeah, how strong the relationship is. Right? This is what the correlation talks about. But the covariance talks about if a unit change in one of the variables, how your relation is affecting towards the relevant change in the other variable. This is about a change of the data between two variables, the covariance. But correlation is purely about the relationship. Okay. Even if you look at the covariance matrix also, it tells the same. Your volume and weight are highly correlated. Yeah. A package called CAR, Companion to Applied Regression. I'm building a plot of model.car.
What is this Corp Core package?
Car package is for understanding the covariance of among the input variables, all the variables in your data. In cars, we have all the input variable as well as the output variable, right? If I just apply car2p car of correlation of the cars, it talks about the covariance. Covariance is nothing but if a unit change in one of the variables and how the relationship between the two variables looks as per the change that is taking place in the first variable versus the expected change in the second variable. It's about the movement, a change of the values, how the relationship will change. Okay. And both of them would reflect the same. But the difference between correlation and covariance, we will see in further sessions in other algorithms. Okay.
Okay.
Yeah. So I'm building a plot of this model.car. Model.car is nothing but my base model, where I considered all the 4 input variables and the output variable, MPG. So this is the model.car, right? Let me draw the plot. You just need to keep hitting the enter in the console window. First time hitting the enter, first time. So it generated one graph. This graph is about the residuals versus fitted plot. What are residuals? Nothing but errors, right? The difference between your actual values and predicted values. What are fitted values? No, nothing but the predicted values, right? This line is different. Don't just think this is the line which represents the predicted line. The equation, what we derive out of OLS, on that line, you will have the predicted values. Okay. This plot is all about how residuals are looking versus the predicted values, fitted values. But generally, just apply your common sense. So you're using an equation to predict certain value. And later on, you are comparing how deviating your predicted value from the actual value. Thereby, you are getting the residuals of the errors. If you just take these predicted values and residuals, how they should reflect as a plot. Residuals, we are talking about the mean. The mean of the residuals is nothing but 0, right? We draw a line which is exactly at the 0, which is the mean. All these data points should fall very closely towards the 0, very tightly. That only then, that means you are making very less mistake in your prediction. If these data points are very close by to this 0 line, that means you are making very little mistake in your prediction. That means your errors are very minimal. The error values are very minimal, right? Alongside of the assumptions what we discussed for each of the sections, the predictors, parameters, errors, and observations, even these also needs to be satisfied if you need to take a model for further consideration. Okay. Now, we are not yet done. I just executed this plot of the base model which we built. I'm hitting enter again. So it generated another graph. Which plot is this? QQ plot. What does it tell? Linearity. There's a QQ plot between of the standardized residuals. Standardized residuals. How do you standardize a value? Residuals are nothing but the errors. How do you standardize the value? Which formula do you need to use? G value, right? G formula. X minus mu by sigma. If you standardize the residuals, nothing but the errors, they should follow normality. Are they following normality by looking at this graph? More or less. The data points which are there in the IQR region, more or less they're falling on the line, right? What does QQ plot give? There's a graph between standardized residuals and fitted values. How they should look like? The standardized residuals and fitted values, how they should look like? They should be very much close by, but you have few observations. These are nothing but the observations which are influencing the overall prediction of the model. Because of the data, the way you have the data in your data set, these observations are influencing your predictions. That's where the predictions are not that accurate enough. Your R squared value, multiple R squared value is 77% for the base model we built. We're still wrong by 23%. That is big, that could be because of these influence, the observations which are influencing. Okay, we need to check whether they're really influencing. Okay, can I remove the observation only rather than remove the entire column? If I remove the entire column, how many data points I will lose? 81. Yeah, 81 are the observations. Between volume and weight, if I find out one of the most insignificant variable, and if I decide to remove that, how many data points will I lose? 81. 81 data points I will lose. But rather, if I know what are the observations that are influencing my overall prediction, if I just remove the 77th observation, how many data points I will lose? 5, right? So that's where you need to take a better decision. Removing the data, losing the data is a very costliest effort. Now, to understand what, if at all, I have any observations that are influencing my overall prediction. There's something called influence index plot. I'm running this influence index plot on the model.car. This influence index plot tells you whichever the observations that are actually beyond this region, the line which you are seeing here, right, the dotted line, beyond this region are a definite influencers. So if you'd like to improve the model's performance, so the first observation that you need to delete is 77 as per influence index plot. And the next one is 79. Clear? This is what the influence index plot tells us. Influence plot, influence index plot, influence plot. Index, you are getting the index number of the respective observations which are influencing. If you just say influence plot, this is how the plot looks like. Even the influence plot clearly saying the 77th observation is not helping for your prediction, right? Yeah. So first one is 77th. Just remove 77, see if it is not improving. Next, you can remove 71, right? Now, let's remove the 77th observation and build the model again, considering all variables as the input variables. Now, let's see the summary of it. I removed a variable, sorry, I removed an observation or row. Sorry, is there a question? Yes, there is some background noise. Could you please go on mute? Yeah, thank you. So I removed an observation. Now, is there any improvement in this model? What is the improvement you are seeing? The multiple R squared value is almost reaching 82, 81.9, right? It's almost 82. It was 77, right? Just by removing one observation, there's so much of increase in your accuracy of the model. But still, can I consider this model? Because still the volume and weight are still insignificant, right? As long as they are insignificant, that means they're not helping me together for a better prediction when I take both of them together into my equation. Okay. Something called VIF, variance inflation factor, to understand the collinearity existing between the variables. Since we are talking about the collinearity, so collinearity, will it be between the input variables or along with the output variable? Collinearity problem exists only between the input variables, right? Just calculating the VIF. So generally, the base thumb rule, whichever the variable has got a VIF value of more than 10, that tends to follow a collinearity problem. So we can, if at all you need to drop off a particular variable, it would be that variable which is having a VIF value of more than 10. But here, all all the variables are having more than 10. If you look at the volume and weight, they're having with the highest values. So we are not getting a hint in terms of which one to drop or which one to retain. So what you can do is, I'm building 4 different models where in the first model, I'm considering weight as the output variable, considering remaining 3 as the input variable. I keep changing so that I have 4 different models for predicting 4 of these variables by using the other 3 variables. Like, look at the summary of it. First, weight. So I'm predicting weight by using all other variables. So are all the variables are significant? All of them are significant or not? No, right? So only volume is significant. Horsepower and speed are not significant. But if you look at the model's performance, that is 99. Let's look at the volume model. For predicting volume, weight is actually helping. But other 2 are not significant. Let's see how HP and speed models are showing. In case of predicting the HP, only speed is helping. Here, volume and weight are insignificant. And similarly, predicting the speed, HP is helping, volume and weight are insignificant. Right? So since we are not getting any hint in terms of what variable I can actually go ahead and remove. Guys, actually speaking, you need to try with removing all the influenced observations, one after the other, and see if the model's performance is improving or not. Let's say if you're not getting any clear indication of the increment in the model's performance, then finally we can check with added variable plots. Added variable plots tell us when you add a variable with other input variables, how it is helping towards the output prediction. AV plots. The way you need to read this, just give me a second. Way you need to read this plot is the first chart talks about when volume is mixed with other input variables, how it is helping for the mileage prediction. Right? When horsepower is mixed with other input variables, how it is helping. When speed is mixed with other variables, considered along with other input variables, how it is helping with the mileage prediction. When weight is included, what kind of impact that is having on the output variable mileage prediction. But wherever the graph that is having a slant or a slope, that means that variable is actually helping in the output variable prediction. But if you look at the graphs, the second one and third one, there are the clear slope existing in that lines. But if you look at the first and fourth, in case of volume, there is a slight slope, very slight, very minimal. But in case of weight, it is almost exactly on the line 0. That means weight is not at all helpful towards the MPC prediction. Okay. And now, only after removing all the influence measures, the observations which are influencing, only after trying out all these things, finally this should be your option. Okay. It's about the order that you follow. Okay. So generally, yeah, you can make use of this. We are not denying it. We are just introducing you something which will be helpful for your prediction. But generally, this is the data set which has got all these problems. This data set has been selected intentionally to let you introduce to all these situations and how do you solve this kind of problems. Okay. Normally, if you take any data set, you don't get to see all these problems. Yeah, you can use any of it in which order you feel like. And obviously the result, you would go based on the result that you get out of each and every experiment that you perform, right? But what I'm saying is, for deleting a variable shouldn't be the option at the first place. Because by deleting a variable, you're losing so much of data. Okay. If at all all other experiments are not helping you, finally, even before deleting, please check the IV plots to understand which variable to delete. Okay. Now, alongside of this, so once you reach to a kind of moderate performing model, then just to cross-check the results, you can make use of, there's a function called step AIC. AIC is for archaic information criteria. You need to load this package called mass to work with this. The step AIC of any model that you are building. Step AIC function automatically understands how your data looks like, and based on that, it gives you the results of various models by default on its own. It has given me two results, two models. The first model has got all 4 input variables. Okay. With this, the AIC value, archaic information criteria value, is 248.06. But in the second model that is proposed, it has removed the weight variable. It has considered only the remaining 3 input variables. Now the step AIC value is 246. Whenever you have multiple models, to compare the performance of the models, your AIC and BIC. AIC is archaic information criteria. BIC is Bayesian information criteria. These two measures would be helpful to pick the best performing model. But how should you pick the best performing model? Whichever the model has got the least AIC and least BIC values. And that model tends to perform better than others. Okay, that interpretation is important. You need to choose a model which has got the least values of AIC and BIC. Okay. Now we are finally building a model. We have decided to drop the weight column, weight variable, building a model by removing the weight. Let's see whether the models. Now, all the variables are significant now. All the coefficients are significant. That's right. They're all significant. How about the overall model significance? Even the overall model level p-value is also lesser than your significance level. So then the entire model result is also significant. but the accuracy is not that better. 77. Okay. How can you improve the accuracy of the model? By applying transformation. Please try out applying various transformation techniques on this finalized model to improve the accuracy of the model. What are the mathematical expressions? The formulas that you apply as part of transformation. Instead of x, take x square or log of x or exponential of x, or 1 by x, 1 by square root of x, or x plus x square. Okay. Try out Johnson transformation. Try out Box-Cox transformation. Okay. Please try to improve the model's performance. And that will be a very good way for you to get hands-on with respect to how do you frame these models and how do you analyze the results. Okay. Please take that as an assignment and try to improve the model's performance. Okay. So this is about multiple linear regression with R. Okay. So let's take a short break and let's come back by 4:30. Okay. 4:30 or 4:25. Anything should be fine. Let's come back and we will discuss, we'll continue with the Python part of it for multiple linear regression. Online folks, are you with me? Okay. Let us start then. Let's look at the Python part of the multiple linear regression. Okay. Fine. Let us import the basic libraries that we need. Python, pandas. Yes, of course, we need this to load the data, to manipulate the data, to perform various operations on the data, right? And NumPy for basic arithmetic operations, Matplotlib for basic visualizations. I'm loading the same data set, cars.csv. 81 observations and 5 rows or 5 columns variables. The top 10 rows, if you'd like to see. Yeah. Top 40 rows here. And for drawing a correlation matrix, the function is .corr and the braces. It gives you the correlation matrix that we already see, where volume and weight are getting into high relationship. And Seaborn, why do we use the Seaborn library? Advanced visualizations. Matplotlib for basic visualization, Seaborn for advanced visualization. The pay plots, what we are drawing, so it gives the distribution of the respective variable, and you can look at either the bottom part of it or the upper part of it. Both are the mirror images. I'm loading stat models, the library stat models, using this OLS. This OLS technique is part of the stat models in Python. OLS is used and the basic model that we're building. Y tilde all input variables. What are the parameters, friends? In the regression equation, what are the parameters? Beta naught, beta 1. All coefficients can also be called as parameters or estimates. These are the intercept value and the coefficient value for all the 4 input variables. And if you do this summary, it gives the complete result of the model. Dot summary. Dot summary of. And gives what is the dependent variable and what is the model that you're using, OLS, what is the method, least squares method, what is the overall accuracy, R squared value, adjusted R squared value, and the overall model's significance, P value. And are all these variables are significant in this? How do you check? The P values. Weight and volume are not significant. Alongside of this, you will get this AIC value and BAC value as well. Archaic information criteria and Bayesian information criteria. Now we are checking individually whether volume is having a relationship with how it is contributing towards the MPC prediction and looking at the summary of it. If you consider volume alone, that is significant, right? And the overall model's performance is very low, 28. And similarly, you can check with weight. And when you bring weight and volume together, both of them are becoming insignificant, right? For drawing the influence plots, why do we use the influence plots? To determine, not the outliers, to determine the observations which are influencing the overall model's performance. As part of stat models graphics. So here, by looking at this, 76th observation seems to be highly influenced. Why it is 76 when we checked it in R 77, right? Why it is given 76? The indexing starts with 0 in Python, right? In Python, 76 means actually it is 77. Okay. Yeah. We are dropping off the 76 and 78. We are applying this at the row level. And applying this overall equation, including all independent variables, again on the new data set after removing the 2 observations. These are the coefficients. This is the overall model summary. Are the variables significant? Coefficients are significant. Still, the weight and volume are not significant. But the model's performance has increased to 84. If you remember, when we removed the 77th observation alone, the model's performance improved till 83, 83.9 something. By removing another influenced observation, it is touching 85. Okay. You can just try out by removing the other observations which are influencing, another 2 or 3, and see if the variables become significant. For generating the predicted values, you just need to use the model and dot predict of the data set on which you would like to run this. Now, for calculating the VAF values, variance inflation factor of HP, considering all other input variables, you're capturing the R-squared value for this equation. VAF, the formula is 1 by 1 minus R-squared value. Mathematical formula is 1 by 1 minus R-squared value. Now, what is the value of VAF HP? 16, right? So you need to check for all the independent variables, if at all, to understand which one is actually having the highest influence. To check for collinearity, right? Then VAF plots. Sorry, this is a data frame. Let me just run this. This is a VAF for weight, VAF for volume, VAF for SP. So I'm capturing all of them into your data frame, the VAF values. Simply creating two variables and the respective values. Converting this into a data frame. And if you see the frame, now it shows the VAF values for each of the model that we built. Now added variable plot to identify which variable is helping the least towards the prediction. Weight versus other variables, intercept with other variables, HP with other variables, volume with other variables. Weight seems to be very much parallel to this 0, right? Based on that, you can take a decision which variable to be removed. Finally, we are removing the weight and building the final model. The parameters, nothing but the coefficients, the overall summary of the model. All of them are significant. And the overall model's performance is 85. How did we get that? We were using, after removing the two highly influential observations. That's why we're getting 85. Okay. So now this is the final model. Let's consider this as the final model that we would like to take it further. So how do we check the other aspects of it? We are generating the predictions on the car's new data by using this final model, whatever we built just now. Importing stats model API, taking the part regress git. This is nothing but added variable plots of the final model. When I remove weight from the equation, see to what extent volume is helping in MPC prediction. The slope is very high. Earlier it was very thin, right? Now to check the linearity, you need to draw a plot between observed values and fitted values. What are the observed values? Actual values given in your data set. And if you draw a plot between observed values and fitted values, fitted are nothing but predicted values. How the graph should look like? Ideally very close by. The prediction should be very much closer to the actuals, right? Somewhat better, not that bad. Still, if you remove the other outliers or the observations which are having highest influence, you can still improve the model's performance. Or you can try out with various transformation techniques. Yeah. Now we'll also see the residuals versus fitted values. Okay, residual versus fitted values, they should be symmetrically distributed across the mean zero. Because of there are some outliers you are observing here, because of which these predictions are not that to that extent that accurate. Okay. If we draw the histogram of these residuals, even if you draw the histogram of the residuals, how it should look like? They should be normally distributed. Okay. Histogram is basically to understand the shape of the data. Drawing the QQ plot, the probability plot between the final model, the residuals from final model based on the distance, normal distance. To check if the data is following normality. If the data is following normality, more or less it is very much onto the line, right? Maybe if we can improve the model's performance, you would get to see even closer. The data points might be very close to the line. Then to check the homoscedasticity, the variance. How do we check the variance? Variance of errors, right? Just plotting a scatter plot of the predicted values and the residuals. Are they homoscedastic? The variance is same. No, right? So this is not satisfied. Others are almost more or less satisfied, but this particular assumption or property is not satisfied. So hence you would need to still need to remove the other influential observations. Thereby you might improve. Okay. try out both, not together. See, whenever you are talking about the possibilities, your number of models, the resultant models will become exponential. One try with transformation, the other one try with by removing the highly influential observation. And if you don't see any further improvement, even after removing the next highest influential observation, then you apply transformation on that data where you already removed the most 2 or 3 influential observations. Okay. There's no point in trying out where you are not getting the results, where you are not able to increase the performance of the model, right? Now, now let's talk about, did we talk about the data partitioning? No, right? Just pay attention here, friends. Data partitioning. What exactly is the data partition? Now, based on the business problem, you understand what all the features needs to be taken into consideration. Through the feature engineering, you finalize the variables that you would like to consider for the model building. And of course, there are various statistical measures that you can take into consideration to check whether the variables you have considered are relevant for your prediction or not, like through forward selection, backward elimination. In all these cases, you make use of adjusted R square, right? As we discussed. Now, whatever the data you manage to extract over a period of time, this has to be in line with what you are predicting. What is your business problem? In terms of, let's say you would like to forecast the sales for next 1 year. What do you think is the relevant time frame of the historical data you need to take into consideration? At least if you have in the last 3-4 years of data, that will be helpful for you to predict for next 1 year, right? And similarly, if you'd like to predict if the customers who are going to default in next 1 month on a loan repayment, because loan repayment, the loans industry is evolving very fastly, right? You might not find the same relevant trend in last year's same month because there is a lot of changes that are happening in the industry. There might be a new policy introduced. There will be a new way of issuing the loans. Okay, a better way of tracking your CIBILs. All these things are coming into the picture. So you might find very higher relationship with your immediate data than your historical data of last year and so on. So based on the business problem you are solving and the kind of industry you're working in, you need to choose the time frame for which the historical data needs to be collected. More and more the data is available, the better. Okay, but when it comes to the number of features, yes, you definitely need to be confined only to the relevant features. But if we grow in terms of the rows, there is no harm because of the computational power that is available to us right now is able to handle that level of volumes. Unless you are growing on the variables of the columns, if you're growing on the rows, still you can handle that load with the current infrastructure that's being provided. Okay, so once you take the historical data, now what do you prefer? Do you prefer to build a model on the complete data that you have taken? You prefer, right? Okay, let's say you have taken the complete data for training your model and you have observed the aspect. Let's say we are solving multiple linear regression. and you came out of the predicted values. You checked all these assumptions. Everything is satisfied. Now, so can you deploy this model into the production? Yeah, obviously. Let's say whatever the assumptions we talked about, you already validated all of them. Residuals was fitted values, observed values with fitted values. How the distribution of the errors looks like. Everything you checked. All the assumptions are satisfied. Okay. So now can you deploy this model into the production? You are ready, right? But let's say if I just move the model into the production, if I get to see the model's performance is very poor for the next 1 month in the production, what do you think the reason would be? Okay, if at all there is a complete change from the business side, which could impact the problem you are solving, you can't do anything, right? Other than that, see, why did we build a multiple linear regression model? We built it to predict the mileage of a vehicle based on other 3 parameters as part of the finalized model. Considering the volume, speed, and horsepower, we built a model. Thereby, we can predict mileage to the better extent. But there is also a possibility that your model could fail because of the reason that whatever the time frame that you are taking into consideration for capturing historical data that you have used for training your model may not have a representation of the patterns or the trends that you might be seeing in the production in recent days. If the historical data is not a representative of similar trends or similar patterns that which you are going to see in the production, then obviously your model tend to fail, right? But how do you counter these kind of issues? That's where it is not always suggested to make use of the entire historical data for training your model. You will not know how this model would perform on some data which is not used for training this model. Because the data which is going to flow in the production, you don't have any sort of control on that. You're not seeing that data so far. Your model is also seeing the data for the first time. What is the guarantee that it might not fail? So just to counter that problem, it is always suggested to partition the historical data into training data, and test data. How do you partition the data to training and test? What is the technique you will use to split this data? It could be anything. You can assign 60% of your historical data to training, 60-40, 70-30, 80-20, 90-10, or sometimes you might go for in the reverse way as well. You might assign only 40% of the data to training, 60% you kept it for testing the performance of the model, right? But how do you split the data into training and test? Do you split the first 60% of the data as train and the remaining 40% of the data into test? Ideally, it should be random. if you take the randomness, if you pick these number of records randomly into these data sets, training data and test data, that makes sure to have a representation of all possible trends. Okay, that's one way. And otherwise, if you're forecasting the sales for next 1 year, let's say you think the last 4 years of sales data is good enough for me. In case of wherever the time is associated with your data, then it is always suggested to keep the most recent data towards the test and prior data towards the training, so that you get a chance to test the performance of your model with the most recent data. Thereby, it gives a confidence, like whether this model can perform when you push it into the production. Okay. Now, we manage to partition the data through whatever the technique we feel relevant. The 60-40, 70-30, and whatever. It could be randomly based, or it could be some proportion-based fix. Okay. Now, we make use of the training data to train the model. We come out with model 1. By using training data, we train the model 1. Then we gauge the performance of this model on the training data first. And we evaluate it. We get to see the accuracy and errors, right? Like R-squared value, RMSE value. Yeah. Then we capture that information. And the model which you come out with, the reasonably performing model that you came out with, by using training data, are called as candidate models or prototype models. And now, can we push this model directly into production? We have to validate it. So we run this model on the validation data or test data to gauge the performance of how these accuracy and errors are looking like on the test data. The accuracy and error that you capture on training are called as test training accuracy and training error. And the same measures what you capture on the test data are called as test accuracy and test errors. And there shouldn't be too much of difference between the accuracies and errors between training and test. Okay. Only by gauging the performance of your model on the test data, if you are satisfied, then you are suggested to go ahead and push this model into the production. Because the model which you are training is not exposed to the test data while training. It doesn't know how the data looks like that you have in the test. So the test data is a complete new set of data as long as the model is concerned, as far as the model is concerned. And that's the whole reason that we suggest always partition the data into training and test to gauge the performance of the models before even taking them for final consult. Am I clear?
One question I have, can I ask?
Yeah, you can.
You mentioned that in case of a time associated, a time series, the most recent data has to be trained data or tested data, most recent one.
Let us say you're predicting sales for next 1 year. And you have captured the data from January 2014 till, let's say, December 2019. Okay.
Okay.
So consider the most recent data. At least make sure you have a 3:1 proportion between training and test, so that you assign the first 3 years of data to train, and the very recent 1 year of data for test.
Okay, got it. Thank you.
Yeah. Now, we are partitioning the data. To partition the data in Python, we have a library called train test split, which is part of sklearn model selection. Importing that library. By using train test split, I'm allocating 0.2 of data to test size. What does that mean? I'm giving 20% of the data to test. So the remaining 80% will be in the train. Hence, this order also matters, friends. First has to be training parameter, training variable. Second one should be the test variable. Okay. So let me partition this data. I'm partitioning it on the car's new data. So the moment I partition, more variables will be created. If you observe here, the car's train data has got 63 observations and car's test data has got 16 observations as per 80-20 split. So we are again training the model on the training data. Building a model on the train data only. This time I'm using only cars underscore train data. So let's see the summary of it, the result. All the variables are significant, coefficients. All of them are right. But how about intercept value? Is more than 0.05, right? It is still fine if the intercept value is little higher. But you need to make sure at least the coefficients of the variables have to be significant. Okay. There is no such threshold. Generally, it will be significant. In certain cases, like because this is a type of data where it has got a whole list of problems already part of this data. And that's the reason you are seeing all this. But generally, it will be within the limits of your significance level. Now, overall model significance is also good. The overall model's p-value is also lesser than your alpha. And look at the R-squared value and adjusted R-squared value. What has happened? It has increased. It was 84.5, right? Now it has increased to 87%. And AAC, BAC values, you need to capture all these values because we are going to compare which model is going to be better across a list of models. That's where you need to capture all these. Now, we built a model on the training. Let's predict the values of MPZ by using this new model what we built. We are predicting based on the training data itself. Now, let's capture the residuals. How do we calculate the residuals? The difference between actuals and predicted values. And these are the residuals. And when we're talking about the errors, so you have a list of observations. So let's say these are the observations. 1, 2, and so on. And for each observation, you will have error because there will be difference between the actual values and predicted values of the output value, output variable. You'll have error for 1, first observation, error for 2, and so on. right? Now, can I straight away compare? Because now we are trying to compare the model's performance between the training data and test data. These are all the errors I captured on the training data. Does it really make sense to compare each observation error between training and test? We have 63 observations here in training. In test, the data is same between training and test? No, right? It's altogether a different data. How can we compare? And that's where there are some error measures that you can rely upon to compare very easily between training and test. What are those error measures? Now you have all the errors, right? Take a square of the error. By the way, what should be the sum of the errors? Assumptions. What should be the sum of the errors? Mean of the errors. Mean will be 0. Take all these errors and square it. It becomes squared errors. Then apply mean on that. Divided by mean is nothing but number of observations. Then apply a square root. Simple words, this is called as, this measure is called as RMSE. You need to read from right to left. You're taking the errors first, you're squaring them, squaring each of the errors. Squaring, you're simply applying E1 square, E2 square, and so on. Once you're done with squaring all the errors, simply taking a mean of it, right? That becomes mean squared error. On top of mean squared value, you're going to apply a square root. So that becomes root mean squared error, RMSE. So we are capturing this RMSE value on the errors we got on the training data for the model we built using training data. Am I clear? Online folks? Am I clear, friends? So to capture, there are no inbuilt functions, the RMSE values. That's why I've already captured the residuals by taking a difference between predicted values and actual values. And then I'm squaring it. Residuals into residuals is nothing but the square of it. And applying a mean of it. And then applying the square root. Capturing that into the training RMSE variable. Here, now we have the training accuracy, which is nothing but the multiple R squared value, and training error, which is nothing but RMSE value on the training data. Now, let's use this model, same model what we built, and run the predictions on the test data. Now we need to see how best it is performing on the unseen data, which is nothing but the test data, right? So let's run this on the test data. And let's capture the residuals on the test data. The moment you run the model, you'll have the predictions generated, take the difference of predicted values on the test data with actual values of test data. That give you the residuals. Then capture test RMSE. Nothing but take the square of the test errors, then apply mean, then apply square root. Clear? Now, what is the training RMS you got? 3.3667. Let's check the test accuracy, test RMS, 4.52. Not that far away, very much close by. But what is our training accuracy? $87, right? R squared value. But this time, let's run it on the cars dot underscore test. What is the accuracy we got on test? 80.7. So training accuracy, or let's say, just a second. These are accuracies. These are the RMSE value. This is training data, and this is test data. What is the training accuracy we got? 87, right? And the test accuracy? 80.7 or 81. Training RMSE value? 3.36. Error for test? 4.45 or something. Right? Do you think the model is reasonably performing even on the test data which is not used for training the model? Almost okay, close by. Because we have taken very small data set to get to see this much of difference. But generally, when you take a huge data in real time, you don't get to see so much of gap if the model is proved to be performing well. But there is also a possibility that let's say, and these are the actual results that we got by testing the model. Let us say the accuracy that you got on the while training the model is 95%, 0.95. But when you run the same model and test, let's say it is giving 70. Can you consider that model for further analysis? No, right? So that means what has happened? While training the model, you have made the model so specific so that it can work very well on the data that you are using for training. But the same model, when it is exposed to the unseen data or the test data, that fails to perform the same level to the same level, right? And this is called a problem called overfitting. Overfitting. That means your model is overfitted towards the training data, but it fails to perform to the same level on the unseen data or test data. This is a problem that we need to deal with. How do we deal with that kind of problems? We will speak in further sessions. But let's take the other example. Let's say when you build the model on training, the accuracy that you got is 60. And when you run the same model on test, the accuracy that you are getting is 55. So the accuracies are more or less close by between training and test. Now, can you take this model for further analysis? No? Why? Exactly. So there is still a lot of scope for you to improve the model's performance on the training itself, right? And this problem is called underfitting. Overfitting and underfitting. Underfitting is something which you get to understand at the first level while gauging the performance of the model on the training data itself. If you are not satisfied yourself with the results that it is giving, there is no point in testing it on the test data. But overfitting is a very dangerous problem. Most of the times you get into these kind of overfitting problems. You obviously will have pressure from the business end to build a model which is working to the most accurate level. You will do all gimmicks, right? In terms of you transform, you apply some complex transformations. Yeah, you check the influence variables, influence plots, AV plots. By doing all this, somehow you got to get an accuracy of 99% on the training data. But fortunately, when you test this model on the test data, it's giving good result, 97%. So obviously, you will go with the flying wings to the business and say that just take the best ever performing model you can deploy. But when it starts running in the production, it might fail as well. Because it is also very important to make sure the test data shouldn't be an exact replica of a subset of your training data. And obviously, when the business keeps running over a time frame, there will be different trends that you would observe at different phases of a time frame. And generally, you don't get into that kind of situation. But when a model is performing too good on the training data, and if you get to see that it's not performing on the test data, that's a typical case of overfitting problem. Then how do we deal with? We will see in further session. When we discuss about lasso and ridge regression, we will talk about that in detail. Okay. But the model which we built just now is actually giving 87% accuracy on the training and 81% accuracy on the test. Since the data volume is very low, I'm very happy with this kind of result. Let's just assume. So that means my model is not fitted or is not specific to the training data. it is still performing good on the other data which is not used for training. Am I clear? So then that is an ideal model that you should have, which is called generalized model. Okay. Overfitting and underfitting are the problems that you need to deal with. But generalized model is the expected behavior of the finalized model. Am I clear? Online folks, any questions so far?
No.
Okay. That's perfectly fine. So we have another half an hour. So what we will do is we'll cover another small topic, but which is again relevant to complete machine learning models, algorithms. So now that's perfectly fine. Now you have built this model. If I ask you to deploy this model into the production, how do you do this? Flask for Python, and or you don't know? Okay. Did you ever deploy any models? Okay, fine. Yeah, Flask is obviously that can be used to deploy these Python models. But these are not the only deployment approaches that are existing. It's purely dependent on the environment you are working, how your data is being saved, in what tools your data is being captured. Okay, and what kind of infrastructure you have. Are you on-premise or are you on cloud? So based on all these things, the deployment approaches and the strategies would change. The deployment architecture that you need to draft would change according to that. So when it comes to that level, you can discuss with the technical architects who are very much aware within the teams about the complete end-to-end system, and sitting along with them, you can draft a strategy. Okay. But if the business asks you, okay, that's perfectly fine, you built a model, you are done with that. How can I make use of the predictions of this model from tomorrow onwards? So to hand over to the non-technical people, so what you can do is you can make use of R Shining to deploy R models, Flask for deploying Python models. Now let us see how do we deploy the R model first. Even before that, I would request you guys to spend some time in reading about what exactly is R Shining. How do you deploy an R code or R model by using R Shining? In which ways I'm going to show you. But what is Flask? How can you integrate with what all the environment it could support? Okay. Now, this is the package that we are going to use in R to deploy the R model that we built. You need to load this library, Shiny. But when you're doing it for the first time, you need to install the packages first. After that, you need to load this Shiny package. Now, using R Shiny, I'm building a fluid page. What do you mean by fluid page technically? A web interface that is flexible towards the change that takes place. Okay, creating a fluid page. This is the function. Within this fluid page, there are two sections. One is sidebar layout and sidebar panel. Panel is within a layout, whatever the fields that you would like to display, they are part of the panel. The layout is what all variables you would like to display together as part of a single block. Okay. So now, how many input variables we have in the cars data set? Overall, originally. Input variables. Input 4, right? Except mileage, all remaining 4 are input variables, independent variables, right? So I'm creating 4 variables, which are of type numeric. Okay. Using numeric input function. So this is my UI layout. When I have values for all of this, so I'm just creating a UI fluid page with all this, all 4 input variables. Just a simple function, right? Now, and this is where the main part is. I'm reading the data from a designated location, right? The CSV, cars.csv. And once I have that, I'm building a model. And then I'm mapping to the original 4 input variables that I declared here, num1, num2, num3. I'm assigning HP values to num. This num1 to volume, num2 to speed, num3 for weight, right? Then I'm predicting this and capturing the predicted values into the variable called W. And finally, I'm writing this W as an output because those are the predictions, right? This is another simple function which contains the input as well as output. So we are reading the input from the CSV we are taking. We are writing back the output. Finally, I'm executing a simple function called Shiny app with 2 arguments. One is what is the UI and what is the server. UI is nothing but the layout which I created. What is the layout in which I have to display, and what should be the overall values that I need to display. So when you execute the server function, what would be the return values towards the end? Nothing but the W values, nothing but the predicted values, right? So when all these 4 input variables, these names and variable names, everything you can change as per the business problem what you are solving. Okay. When all these values are 1, 1, 1, the predicted value based on the formula which you built is, based on the regression equation that you built is 30.93. If the business team wants to check what would be the predicted value of mileage if one of the variables is this, then accordingly your output variable, the predicted value would change as per the equation, right? So if you hand over this kind of setup, a simple web-based deployment, the business teams, that will be very handy for them. And alongside of this, generally, whatever the dashboards you built using Tableau or whoever that visualization engineers are there, they can associate their dashboards along with your in this web page. Okay. So simple, very straightforward deployment. But still, even for deploying the complex models, you can still use RShiny. But RShiny is licensed. Okay. But I think you still have the open source version, but it has got very limited capabilities. You can include the graphs and everything so that it makes interesting for the business teams. Okay. This is about deploying your R codes. Now let us see how do we deploy the Python codes. Flask. What is the Flask? It's basically an integrated API that is available for you to deploy your models in a very easy, pluggable manner. Spend some time in terms of reading about what all capabilities it has got. What are the different ways of deployments that you can do with this particular tool, Flask? It's basically an API. Okay. All these packages are the libraries that you're using either in R or Python. They're all APIs. Okay. First, importing Flask, render template, URL for request. And these are all the libraries I'm importing from Flask. Along with that, I need pandas to read the data. Pickle. Pickle means what is pickle means? Normal programming terms. Segregation, right? Whatever the output you are going to get through the process, through the lines of code that you are writing, you will segregate and pickle it as one group, and you will make use of it for any further display. Linear regression, of course, we are using that for predicting the cars mileage. We are using linear regression and sklearn external, and also I'm importing this OS to interact with the files that are there in the directories. Okay, for setting up directories, already pointed to that. Okay, first creating a variable called app with the function Flask. The syntax is all these names underscore name underscore. So you can define your own name, whichever you would like to. Now, defining home is the template that I am using. What do I have in home? A similar way, there's a different problem that we are solving, not the cost problem. Different regression problem. There's a market spend and what is the cost that you are spending on the administration. And based on various things, like which state you are actually working for, accordingly, the output is going to display. This is a template I'm using. So I'm rendering the template. And this is where we're actually reading the CSV of 50 startups. The startups is actually located here only. There's nothing but the data that we're dealing with. So based on what is the R&D spend, what is the administration, what is the marketing spend, which state you are working, and based on that, you need to predict the profit. Okay. Why do you think I'm getting the dummy variables here? The state is a categorical data, right? Sorry. State is nothing but a categorical data. That's why I'm creating the dummy variables. and applying a linear regression function because the profit is there's an x comma y format. I'm first dropping this profit from the entire data from all the columns. The remaining I can use as input variable. Then x comma y. Y is nothing but the profit. And based on all these values that are being read from the spreadsheet that we are providing, it follows the conditions. I'm writing the logic here. State equal to Florida, C is equal to 1, F equal to 1. And you write whatever the logic according to your model that you built. Finally, I'm converting this into a data frame of the predicted values. I'm running this model to predict on this data, whatever you're going to give. Because we are not partitioning the data into training and test here. The moment, only during the training process, you partition the data into training and test. But which piece of the code you generally deploy into the production? For multiple linear regression, we have written so much of code, right? Do we need to deploy all of that? The final model underscore final is what there. That's a model you would like to deploy. Which piece of code do you actually write in the production? What is the function we use to produce the output based on a model which we built? Dot predict, right? Model dot predict. Model dot predict and give the location of the file which has to be read as the input data. You don't need to train again every day in the production. Okay. And obviously, if you say this is the model that is finalized, dot predict of the variable in which you have the input data, that's it. We are returning this result, prediction equal to my pred. What do I have in the result? Nothing so far. Just passing in that argument name. Not writable. Show echo. App.root equal to predict slash predict. Result. Home of render home template. Pass name. If name equal to main from work equal to Just mismatch of the names, the functions. You're generating HTML. When is it updated? 11. Some issue with my environment, guys. Just execute this on your machines. It will work. Okay. And this is a simple way of deploying very plain models. Just spend some time reading about what all different ways of deploying the models using Flask as well as R-Shiny. Okay. Which is going to be very useful. Even people are actually extending the Flask implementation to the productions, the corporates. Okay. It's not just for the academics. It's not just for the learning purpose, what we are seeing here. You can extend this. You can configure Flask with your, but only thing is you need to make sure that all the environments that you're working with, all the tools or the softwares are supported by Flask. Okay. Simple CSS scripting that you can write, even to execute or deploy the complex models. Am I clear, guys? Any questions, online folks? Okay. So I'd like to stop here for today. So next Saturday when we meet, we'll discuss about lasso regression, ridge regression, and from there, and after that, we will start with logistic regression, binomial logistic regression, multinomial logistic regression. Okay. Okay, fine, guys. Thanks for attending. See you next week.